When we start to combine the RLC components, we discover that some aspects of the individual components will combine. The combination of those aspects will depend on how we are connecting them, whether they're in series and parallel, or which components we're actually using. Let's start off by looking at the resistor inductor connection. Firstly, in series. Looking at the resistor and the inductor, R and L. In series, we know in series that my current flow is going to be my reference, and as a result, the supply voltage that I connect is going to divide over my resistor and my inductor. Because the supply voltage has a frequency, my inductor is going to generate a reactance that we looked at in part 1. My resistor, because it's series, current is my reference, so my resistor will generate or allow a current flow through it, and the inductor will also allow that same amount of current to flow through it. When it comes to the voltages, however, the inductor or the resistor will generate a voltage that's in phase with the current flow, and the inductor will have the leading voltage because of the back EMF that it generates. When we combine these two, my current is the reference, VR comes from the origin, VL is my vertical, and the result is that we generate my V total at an angle with reference to my current that is being supplied. That's called the phase angle, and we'll look at that at a later stage. Now, we have to remember that the voltages that is generated in a series circuit, those voltages are in phase with the ohmic values that the circuits will have. That will result in the following. XL will be indicated on the vertical, R will be indicated on the horizontal. Now, my total opposition to current, it's called the impedance. My total opposition to current we represent with the Z symbol. Impedance is the total opposition to the flow of a charge or a current in a circuit. Impedance. To calculate the impedance of the circuit, we use the formula Z is equal to R squared plus, in this case, because we've only got the inductor in the circuit, say XL squared, and we can see that we've got Pythagoras in this scenario. Z is my diagonal, R is my horizontal, and XL is the same as that height there, which is my vertical. We can also apply this exact same concept to the voltages in the circuit, and there we can say V total is equal to the square root of the resistance voltage squared plus the inductor's voltage squared. All of that rooted, and that will give me my total voltage. We have to remember that these are still represented by rotating vectors. When it comes to parallel, we're taking again the resistor, but now we're connecting it in parallel with the inductor, and all of this I'm connecting in parallel with the supply voltage. Now we know that the supply voltage is the same as the voltage on the inductor and the voltage on the resistor. Kirchhoff's parallel voltage law. We also know that the current that's going to be delivered by the supply is going to separate into the current through the inductor and the current flow through the resistor. These two will combine to give me a total current value. Now, because the voltage is the reference, when I draw these phasor diagrams, we draw the voltage on the horizontal. V total is the supply voltage, and in both cases V total is the same. When it comes to the currents, my current flow, IR, shown on the horizontal for the resistor, and for the inductor we know that it has a lagging current. So when we take these two phasor diagrams and we combine them, we see that V total lies like that, and then VR is on the horizontal, IR is on the horizontal, and IL is on the vertical, but this time pointing downwards. And when we draw the phasor diagram, we see that the total current, I total, is now at the lagging angle with reference to the voltage that is being supplied. When it comes to parallel circuits, we learned that the total resistance of a parallel circuit will be the inverse of the individual resistances. So when we apply that, we see 1 over Z is equal to the square root of 1 over R squared plus 1 over X total squared, all of that rooted. Because of our Pythagoras occurring again in our phasor diagram, I total is equal to the square root of IR squared, or the resistor's current squared, plus the inductor's current squared, and that gives me my total current. Now, out of experience, this formula could cause hassles when reading into the calculator, so as a result I recommend that whenever possible we say that Z is equal to V total divided by I total. This is the safest route to go, and we always use this formula unless the situation occurs where we cannot use this formula and we have to use that formula.